We now summarize the procedures for converting between polar form and rectangular form for complex numbers. We'll start with conversion from polar form to rectangular form. Suppose that we have a complex number z given by r times CIS of theta, where r is non-negative and theta is at least 0 and less than 2 pi. To convert z to polar form means that we want to find real numbers a and b such that z is equal to a plus b times I. To find a and b, remember that CIS theta is simply an abbreviation for cosine theta plus I times sine theta. So that means z is equal to r times cos theta plus I times sine theta, and that gives us r times cos theta plus r times sine theta times I. And so this is our A and this will be our B. So let's look at an example. Suppose that z is given by the square root of 2 times CIS 3/7. Now we just need to rewrite this as square root of 2 times cosine 3/7 plus the square root of 2 times sine 3/7 times I. Here we're using angles in radians, so if you punch this into the calculator, cosine 3/7 times square root of 2, this will be roughly 1.2863. And if you use the calculator for this will be roughly 0.5877 times I. And that's the rectangular form for z, with real and imaginary parts rounded to 4 decimal places. We now look at conversion from rectangular form to polar form. So suppose that z is given as a plus bi, where a and b are real numbers. And we want to write z as r times CIS theta, where r is the modulus of z, and in this case is simply the square root of a squared plus b squared, and theta to be at least 0 and less than 2 pi. So the question is, how do we find theta? We already know how to find r. Let's first take care of a few special cases. If z is 0, then both a and b are 0. In this case, r here will be 0. Now 0 times whatever is against 0, so there's no restriction on what theta must be. But by convention, we are going to choose theta equal to 0. Next, let's consider the case when a is equal to 0. Now if a is 0, then the complex number lies on the imaginary axis. And if b is positive, that means the complex number is in the positive imaginary axis. So if we look at this sketch, the imaginary number will be somewhere up here. And so the angle here will be pi over 2. Now if b is less than 0, that means the complex number is going to be somewhere down here. The angle in this case will be 3 pi over 2. Next, let's consider the case when b is 0. When b is 0, z is actually a real number, and so as a complex number, it will lie on the real axis. So if a is positive, then the complex number will be somewhere here. And in this case, the angle is 0. And if a is negative, the complex number will be somewhere here. And in this case, the angle will be equal to pi. So now we have 4 more cases to consider. The first of these 4 cases is when a and b are both positive. The second case that we'll consider is a is negative but b is positive. The third case we're going to consider is when both a and b are negative. And the last case we're going to consider is when a is positive and b is negative. I have actually drawn these cases on the complex plane. And that basically tells you the location of the complex number for each of these cases. So for the first case, my complex number is somewhere around here. And the angle that we want to find is this. If we now draw the right angle triangle this way, this is the opposite side, and its length is going to be b, and the base is going to be a. In this case, theta is going to be the inverse tangent of b over a. What if our complex number is here, where a is negative and b is positive? Again, we draw a right angle triangle like this. Now, what we're going to do is we're going to first find this angle. In reality, this is the angle for theta. It's simply pi minus alpha. But what is alpha? Well, alpha is the inverse tangent of the length of the opposite side, which in this case is b, divided by the length of the base, which in this case is negative a, but we'll take the absolute value instead. So alpha is the inverse tangent of b over the absolute value of a, and so theta is pi minus alpha. Now, for this third case here, we do something similar. So my complex number is somewhere down here. And again, we form a right angle triangle. This time, theta, which is this angle here, is going to be pi plus alpha, pi being the angle for the semicircle. So theta is going to be pi plus alpha. But alpha is given by the inverse tangent of the absolute value of b divided by the absolute value of a. The reason is the length of the opposite side is given by the absolute value of b, and the length of the base is given by the absolute value of a. Finally, if my complex number is here, and if this angle is alpha, then theta is given by 2 pi minus alpha. And alpha in this case is the inverse tangent of the absolute value of b divided by a. And in fact, we can summarize these four cases. So let's conclude by looking at one example. So in this case, r is given by the square root of minus 1 squared plus minus 17 squared, and that's equal to the square root of 290. Now for the value theta, we are into this case here. So this is going to be pi plus the inverse tangent of the absolute value of minus 17 divided by the absolute value of minus 1, which is simply pi plus the inverse tangent of 17.